All right, in lesson 36, we're going to take a quick look at satellites. Now, there's a little bit of history here on satellites, of course, the first satellite being Sputnik by the Russians. But really, the first bit of information comes from Newton's cannon. Now, if you did the little demonstration on Newton's cannon ahead of time, you would have basically kind of noticed a couple real basic things here. Now, if we use this as an example here, if you don't give it any velocity, it basically just kind of falls perfectly flat. And you can imagine if you were to give it like almost infinite velocity, that it would basically shoot straight out. Somewhere in between those two, there's a sweet spot, which is basically a certain velocity that is hit where it actually falls at a rate that matches the curvature of the Earth. If it falls at that particular rate, it ends up being a circular orbit. So really, anything between these 2 points here run into an elliptical orbit, which is what most satellites do. They're traveling at some kind of a velocity between the curvature of the Earth and infinite that makes them fall into an elliptical orbit. Obviously, the further it is to infinite, the larger the orbit, so years, millions, hundreds, thousands of years, where if it's closer to the circular one, it's going to be less than 24 hours. Now, if we kind of go on, there's a lot of information that describes that and lets you know what it is. But what happens is this basically results in the use of some formulas. Now, if I quickly jump to our formula sheet, you're using two basic equations here, which is number one, force of gravity. So the force of gravity, if you go back to Newton's universal law of gravitation, is big G, m1, m2 divided by d squared. So the distance are r squared, and the two masses, the Earth and whatever the other object is. Now we're going to basically make this Fg equal to Fc. Jumping down to here, that means you've got two possibilities. That gives you Fc, and that gives you Fc. Then, depending on what you're looking for, you get different variables. Okay? The other one is, which is very quickly, is basically, we're going to look very quickly at this one. That force of gravity is equal to mass times gravity. If we look at the equations that we're going to work with, which is here, here, and here, those two equations, or three equations, are derived from other ones. So this one in particular is basically saying, what's force of gravity? Force of gravity is mass times gravity. It's also equal to big G m1 m2 over r squared or d squared. Now, one of those is like the mass of the Earth, the other one is the mass of the object. If you eliminate that mass from both sides, you're left with this equation here. G is equal to big G m2 over r squared. And this is basically the mass of whatever object is creating that gravity. The most common case is Earth. Now, the other ones are basically, if an object is in orbit, we're basically saying that at that particular point, the Fc is equal to a force of gravity generated by that object, like the Earth, for example. And we just simply combine those two equations. If we look at the very first one, which is V is equal to the square root of big G, mass of Earth over R, all you're doing is taking Fc, which is mv squared over R, is equal to Fc, and you're making that equal to Fg, big G, m1, m2 over R squared. Now, not going into a lot of detail, move R to this side, one of the R's cancel out, boom, boom, boom. It's got a squared value, you end up square rooting it, you end up with that equation there. All I do for this one here is I switch out. If I use this one here instead, m 4 pi squared r over t squared is equal to big G m1 m2 over r squared. Solve for the period of rotation now for a satellite traveling around space, and you end up with, in this particular case, you end up with an r cubed, and again a square root based on the period. And that's where those two equations come from. The majority of satellite motion and the questions and formulas that you have to work with are based on those two equations. Now we can look very quickly. There are a couple examples in the notes, but we're just going to look at one here real quick. Now we're going to look very quickly at example 4. Now in example 4, we're going to look at a geostationary satellite. So this is a satellite that sits at the exact same spot around the Earth the whole time. So as Earth makes a rotation in 24 hours, that satellite makes the exact same rotation. And we want to know how high it is. So we're looking for the distance from the center of the Earth. In particular, we're looking actually for the distance from the surface of the Earth. Now we can actually derive this equation based on the one that was given to you. And I'll just grab a formula sheet and we'll do that real quick. If I start with this equation here, I need to get r. So if we square everything again, I've basically derived the equation that I need. So r is equal to the cube root of big G, mass of the Earth, multiplied by the period squared, over 4 pi squared. Now if we jump back to the notes, yeah, that looks about right. All it is left is plugging in the values. Big G, universal gravitational constant, mass of the Earth, constant, 4 pi squared, pi is a constant, and we do the cube root. Now the one thing that we are missing is t. We do have t of 24 hours, but we got to get that in seconds. So you basically got to multiply that by 60 seconds or 60 minutes to get minutes, and then multiply by 60 again to get seconds, which should work out to that magical number there. We do the math by simply multiplying through, and we end up with this number here. Now it's not quite right because that's the distance from the center of the Earth to where the satellite is. We need to get the distance from here to here. Now to get that, you simply have to subtract the radius of the Earth. That is a constant, should be on your formula sheet. So that number is down here, 6.37 times 10 to the exponent of 6, which is basically about, 6,370 kilometers to the center of the Earth. If we subtract that from the value that we get here, we end up with, 3.59 times 10 to the 7th, which is, instead of 3,000, 36,000 kilometers above the Earth. So we're about basically, 6 kilometers here and 36 kilometers here, in kind of a rough approximation to kind of give you an idea. So 6 versus 36. So 6 times further out than the radius of the Earth. So they're pretty far away. All right. Give some questions here a try that are attached to the worksheet. I'll be honest, it's a little tricky because the math has got square roots and cube roots and those kind of things. So you need to know how to use your calculator, so give it a go. If you have any questions, just come see me and I'll give you some help.